Good morning. It's my pleasure to introduce almost Dr. Sam Root, who will be giving a presentation on molecular dynamics simulations and things that you can do kind of at the next level with molecular modeling using some of the principles that we've been discussing in the class so far. So Sam's a fourth-year PhD student in my group who's defending in February and will be starting a postdoc at Harvard in April. So let's give him a warm welcome.
Thanks, Darren. So I got two mics for this. It's interesting. Everything I learned about intermolecular forces came from Professor Lipomi in this class like 2 years ago. So I've been doing research in Darren's lab, and I've been kind of the computational person within the lab. And so this presentation is just meant to show you guys what can be done with computation and perhaps inspire you to consider it to complement some of your research. So I'll start with just like a basic definition of computational modeling. So it's just the use of computer algorithms to study complex systems that you can't solve analytically. And so this definition comes straight from Wikipedia. Some basic examples are, and these are pretty relevant in modern society, weather forecasting. So pretty much solving fluid mechanics problems on a large scale with experimental data. Cosmology, studying how the universe evolves in time. Finance, this could potentially make you a lot of money. It's particularly difficult to model because it's very random. It's not like physics where you have some governing equation, you know. And then maybe something more relevant to this class would be like quantum mechanical modeling, like solving Schrodinger's equation. But I'm not going to talk about any of these. So why does it matter? So I think for me, the most important thing is trying to bridge our theoretical understanding for what's going on at the nanoscale with our experimental results. So you can use it to test a hypothesis or provide some evidence to support a claim in a paper. Another motivation would be to be able to predict material properties for engineering design. So you can predict various physical properties and use it to maybe pre-screen candidate materials and avoid going into the lab. Try to have a rational design strategy. And then another reason is to just a fundamental investigation of nanoscale phenomena that you just can't study experimentally. It's just there's no tools available to do it. So in that case, you would have to rely on computational modeling. And then just visualization to aid in teaching and dissemination of ideas. So if you make some simulations to support your experimental work, you can show people what's going on in a way that anybody can understand. So I'm actually going to give this presentation. I'm going to get rid of the equations, but I'm going to give this presentation to third graders next week. And I think they'll be able to understand what's going on. Maybe not, I don't know. So there's various approaches to modeling molecular systems. You really can't do it quantum mechanically. You're restricted to things less than like 1,000 electrons when you're doing something quantum mechanically. But so there's two main approaches that people use, and that's not advancing. Okay. The first is called molecular dynamics, and the other is called Monte Carlo. Molecular dynamics is just the numerical solution of Newton's equation of motion, and you just essentially have a numerical scheme where at each time step you update the positions and the velocities of a set of interacting particles and compute the force and iterate. And then Monte Carlo is a biased statistical sampling technique. You sample equilibrium states from some thermodynamic ensemble, and the way that it works is you'll make some random move, and you'll either accept it or reject it according to the Boltzmann distribution. And there's lots of trade-offs between these two approaches, but molecular dynamics is kind of what's like, Monte Carlo seems to be a thing of the past. I mean, it's useful for certain things, but the fact that molecular dynamics can be accelerated with GPUs has really let it take off in recent years. And Monte Carlo is not inherently parallelizable. So, but it's still useful for certain things, and I use it also sometimes. But either way, both require some recipe for computing intermolecular forces, which is what you guys learned in this class. So just a brief review of Newtonian mechanics. You have this Hamiltonian. You have the sum of the kinetic energy of all the interacting particles and the sum of the potential energy. Or the potential energy is a function of the position of all the particles. And you can find the force for a conservative force field. It's just the gradient, negative gradient of the potential energy. You guys learned all about that in this class. And then for a molecular system, usually you'll model it as a state of bonds. So this is like a two-body interaction between atoms. Angles is a three-body interaction. It shows how like a molecule would kind of wiggle like this. And then dihedrals is four-body interaction. It has this kind of rotational between four atoms. And then pairwise interactions, which generally people just use like the Leonard-Jones or electrostatic interactions. So here's the most basic example. It's the Leonard-Jones potential. And what I did was I set up the simulation box. I don't know, maybe like 5,000 atoms. And they're all colored according to their index, so they're all colored separately. And they're given some initial velocity. And then you just let it run. And so you can see entropy occurring. So the blue is going to mix up into the white and the red. And if you let this run indefinitely, you're going to end up with a completely mixed system. So this would be in a constant energy, constant number of particles, and constant volume ensemble. But there's also different ways of doing it. Like we live in constant pressure and constant temperature conditions. So I'll discuss that later. But here's another example. So with this simulation, I have a wall that's defined by like a Leonard-Jones wall. So if you integrate the Leonard-Jones potential over a block, it gives that attractive potential to the wall. So that's what makes the droplet stick, and it forms this contact angle. And if you see when the simulation starts, there's a lot of extra kinetic energy. And all the atoms with a lot of kinetic energy evaporate, and it results in a cooling of the droplet, and then it eventually becomes stable and stops evaporating. So this brings up kind of an important question in how do you control the temperature in an MD simulation? Because we live in constant temperature conditions. Our experiments are generally run under constant temperature, so we need a way of controlling that. And the way that it's done is using something called an equipartition theorem. So it just relates the temperature to the kinetic energy of all the constituent particles. So at each time step in the simulation, you can compute what the temperature is. And then there's various schemes for making it stay at a set point temperature. So the simplest one, if any of you guys are chemical engineers, it'll make very intuitive sense to you, or any engineers. It's like a control theory, like a PID controller. So at each time step, you calculate the velocity, or you calculate the temperature, and you get the difference between the set point and the actual temperature, and then you either rescale it to make it smaller to get to the set point or larger, depending on the difference. And that's really not based on any physical basis. It's just like, you know, an algorithm. But there's more rigorous ways of doing it. One's called Langevin dynamics. So Paul Langevin was a statistical physicist, and he came up with this equation that describes how molecules would move around within a solvent if they have random forces that they're being subjected to, like Brownian motion, and they also have drag. So the way that temperature is introduced here is by the magnitude of the random forces that the particles are subjected to. And this would be used to study like an implicitly solvated system. So if you have like solvent molecules take up a lot of computational energy to simulate. So if you want to, kind of eliminate them from your system, you can just use Langevin dynamics. And then there's another technique that's probably the most rigorous, and it's called a Nuss-Hoover thermostat. And you actually make a modification to Newton's equations of motion to couple your system with an external heat bath. And it's kind of complicated. I wouldn't say I completely understand it, but it's pretty easy to implement. Okay, so I think you guys learned about oscillatory solvation forces. So I thought that was a really cool concept. And I just wanted to make a little simulation to show that. So what I have here is two walls at the top and bottom that are one's pushing down. And so you can see at the end, if I pause it, you see how it forms that, it goes from amorphous, like a liquid structure, and then at the end it forms this crystal. And so the slip between those crystals when you're pushing down is what gives rise to an oscillatory surface force. If you see that I actually can't finish the simulation, what happens at the end is it blows up. It becomes numerically unstable because these potentials are not very accurate under such high pressure conditions. Things become very quantum mechanical at that point. But yeah, so basically if during your simulation, if the force is very large on your particle and your time step is big, the particles are going to leave the simulation box and everything's going to explode. So it's a very dangerous line of work. Here's an example. I'm going to give a couple of like 2D simulations because they take less time to run and they can still kind of show the basic point. So this is just two surface Asperities running past one another, and you can see that there's this, exchange of particles. And so this is just like the atomic basis for friction and abrasion. So like sandpaper. Here's a simulation showing a flow past an obstacle. So you might have learned about this in your fluid mechanics course. It can also be shown with discrete particle dynamics. I colored the particles according to the horizontal component of their force vector. So you can see that there's large forces accumulating at the stagnation point and then low forces in the wake. Okay, this is a kind of cool one. What I have here is just like a 2D solid, crystalline solid, and over here I just shut off the interactions between these particles. And then at time 0, I'm going to pull it apart vertically, and I'm coloring everything according to the force vector. So there's going to be a concentration of stress at the tip of that crack, and you can see how it propagates. Oh, just kidding. So you see how there was like a shock wave that bounced off the walls? Yeah. So that's an effect of a finite system size. So if it was this is, maybe 10 nanometers across, it's not big enough to actually get a realistic simulation of what's going to go down. But it's kind of cool to see the shock waves bouncing off the walls. I think you guys have a project involving dipoles. I hope you guys are having fun with that. So I made this little dipole simulation with like 5,000 atoms. Let's see. I'm not sure why it's forming voids. I think it might have to do with the fact that the volume is not completely equilibrated. So there's another technique that you can control the pressure. So right now this is a constant volume simulation. The walls can't change. But you can introduce a pressure control with methods similar to the way that you control the temperature. That would probably get rid of the voids. But anyway, you can see how the dipoles interact, these little arrows. I think you guys also learned about micelles. So essentially, these white particles interact strongly with one another, and the blue ones interact strongly with the red ones, and they just self-assemble to form these micelle-like structures. And if you wait till the end, they kind of all aggregate, and this could be an example of how a cell membrane would form. It's an interesting example of just dynamic self-assembly. This next simulation is of colloids. So this is the model for this is essentially obtained by integrating the Lennard-Jones potential over a sphere. And then, so the interactions between the colloids are that, and then the solvent are just regular Lennard-Jones atoms. So you can see, if you look closely, you can kind of see like depletion things going on. When particles get close, you know, the solvent molecules will move away. This next one is a liquid crystal simulation, so a liquid crystal within the solvent. So these ellipsoidal particles, it's a kind of a tensor generalization of the Lennard-Jones. So you have different interaction parameters in each dimension of the ellipse, and it also has some angular momentum. So yeah, you can use this to simulate how liquid crystals would self-organize, like a smectic phase or a pneumatic phase. And then these materials hold a special place in my heart, polymers. They like to wiggle around. So this is the basic building blocks for like any molecular system. I think I mentioned were these kind of bonding interactions. So in this case, it's a harmonic bond. You have a harmonic angle and then a dihedral angle, which is like a cosine. And then actually, in this case, I shut off the attractive part of the Lennard-Jones and just use a repulsive part. And that could model how a polymer would be in solution, for example, in a theta solvent. And then once you have these models for the polymers, you can look at, this is an example of a thin film under uniaxial tensile loading. So you can use this to predict how these materials respond to mechanical deformations. This is an example of a coarse grain model for a polymer. So if this was done with, like, if you included all the atoms, like the carbons and the hydrogens, this would be about 25 million atoms. But since I like mapped the atoms to coarse grain beads, that maybe there's like 10 atoms per bead, you can do it in a reasonable amount of time on the supercomputer. This next one is a simulation showing the physical vapor deposition process. So all I'm doing here is shooting gold atoms at a graphene surface and watching how they assemble into these island structures. Okay, so those were kind of the flashy pictures and videos, but there's definitely some limitations to this modeling with anything, and you have to understand your limitations. Your maximum time step is limited by the frequency of the fastest vibrational mode. So for an atomic system, that's on the order of femtoseconds. And so it takes 1 million time steps to do 1 nanosecond. Just to give you guys this kind of fact surprised me when I first heard it. Does anybody know how far light travels in a nanosecond? It's about this far. A nanosecond is an incredibly small amount of time. So that's like the major limitation of molecular dynamics, is the largest time you can simulate is microseconds. I recently saw a paper where they did a full atomistic simulation of HIV virus for like microseconds, and that's using like the fanciest supercomputers, and probably took them a year to do. But these problems can be resolved using coarse-grained models, and also the rate that computational resources are getting better makes it so that it's probably a problem that will be solved by brute force in the future, especially with GPUs. So they're not only useful for mining Bitcoins. So your maximum system size is limited by your computational resources. A laptop, so I actually did all these, all the 2D simulations were just done on my laptop. And you generally limited to 10,000 particles, although your laptop will probably start to get hot. You might want to put it in the fridge, I don't know. On a desktop, you could do 100,000 particles. And then on a supercomputer, depending on how many nodes you're using, you could do up to 1 billion particles. Yeah?
I was curious, would we do a coarse grain model, does that somehow skip over these bond vibration simulations? Like, can we
Yeah, so
time increments, or does it just bundle the atoms?
yeah, it bundles them together so that their bonds occur like on different, it's a bond between a group of atoms instead. So it's the center of mass of a group of atoms. So it has slower bond vibrations. For example, for that coarse grain model, I mapped a thiophene ring, like a carbon ring to a single bead. So you're looking at the vibrations over all of those, centers of masses.
Okay. Sam, can you repeat what the question was?
The question was, when you're using coarse grain models, are you still limited by the frequencies of atomic vibrations? And it's no, because you're getting it's a mean field model. You're integrating out and just treating it as an average. And this is kind of the most important thing. Your predictions are only as good as your model. So if you use a garbage model, you're going to get garbage results. And that's with any type of modeling. So you really need to understand the theory that goes into making the model. You need to know, when is Leonard Jones appropriate? When is it not? And what is the range of applicability of your model? So for all the simulations that I've shown thus far were like some toy models, coarse grain. So you might ask, like, how do you actually simulate a real molecule? And so there's these empirical force fields that you can develop, and they come from both theory, so you can use quantum mechanical simulations to calculate equilibrium bonds, angles, dihedrals, and partial charges. And you can also do experiments. Infrared spectroscopy can give you information about the bond vibration frequencies and the angular vibration frequencies. And you can also use these thermophysical properties to validate your model, so make sure that your model is giving the appropriate predictions before you use it to study something else that you might not be able to look at experimentally. There's a set of standard force fields that exist. These are just to name a few, for example, for organic liquids and polymers. And then this field is very developed for biomolecules. That's probably where the most activity is right now. So this is an example of a real polymer, polyethylene. And what I did was I started out completely straight, and then I'm gradually increasing the temperature. So there's thermal motions being induced, and it turns out that the entropy of the system is maximized when it's in this kind of conformation, not when it's completely straight. And so if you look at the temperature profile for this simulation, it's going to look something like this. So like, let's say this is temperature, and this is time. It goes like this. So I heat it up and then I cool it down, and so right now it's cooling down and it gets kinetically trapped in that folded state. So it can't go back to that original extended state. And this is an example of like a glassy system. So it's, yeah?
So like, how fast did you cool it down? Because if you cooled it slower, would it straighten out perfectly?
Yeah, if you no, it would never, well, if you cooled it like,
Repeat the question.
he was asking how fast was I cooling it, and would it change if I cooled it slower? And the answer is yes. If you cooled it infinitely slowly, it might be able to get back to that straight state, because that's the minimum energy state. But it's just, you would need to go really slowly. And it would never happen, really, in practice. But yeah, if you quench it, it'll just get trapped in whatever state it's in. Okay. And then these are some examples from my research where I made these models, these atomistic models for conjugated polymers, which are particularly difficult to make models for because they have these heterocyclic rings along the backbone.
What's a conjugated polymer and what's a heterocyclic ring?
So a conjugated polymer has pi conjugation all along the backbone. It doesn't have to be a heterocyclic ring, but it turns out that the best ones are heterocyclic rings. So like your most basic conjugated polymers would be this guy. And it has the alternating single double bond motif, so it actually behaves as a semiconductor. Yeah, so these are just the kind of recently developed conjugated polymers that are simulated. And those are fullerenes for all you nano engineers.
Heterocyclic means that it has an atom that's not carbon in the ring.
Okay, yeah. So I made software for doing all these simulations. If anyone's interested in incorporating this into your research, you can come talk to me. You start with quantum mechanical simulations with some molecular fragment. You can make these atomistic models. And then this is the challenging part, making the coarse grain model. But this is software that I'm currently developing. Andrew's helping out. And so, yeah, if anyone's interested, just come talk to me after class. All of these simulations, except for the ones done on my laptop, were done on the local supercomputer. So there's this NSF-funded program called Exceed that you can write proposals and get supercomputer time. And it's really easy, and it's pretty useful. So also, if you're interested in that, I can help point you in the right direction. Oh, okay, now I'm gonna switch gears a little bit and talk about experimental stuff. This is kind of just exciting to me at the moment because of the project I'm working on. So here's an application of surface tension for some physical process. So it turns out when you put a drop of a polymer solution onto the surface of water, it can either spread out and dry and form this polymer film, or it can form this thing called a sessile lens. And that depends on the magnitude of this S parameter. It's called the surface spreading parameter. So if S is greater than 0, there's a net tension force due to that gamma 1 that makes it spread out. And it spreads out to nanometer thickness, like on the order of 50 nanometers. So this idea was really first discovered by Benjamin Franklin when he put a spoon of oil onto a pond and noticed that the waves in the distance were quelled. And then actually it was also used to get the first estimate for a molecular radius by Lord Rayleigh, who did it with hexane and estimated the radius to within a couple, pretty good precision for the 1800s or something. So recently this group published this paper where they used it to make an organic solar cell. So the organic solar cell has this active layer that has to be about 100 nanometers thick. So if you put a drop of this polymer solution on water, it spreads out and then you can stamp it and make a device. And so my idea was to try to turn this into a continuous process for manufacturing. And so the idea is you have this liquid aqueous bath in a vessel with a wall, a hydrophobic wall, so it forms this contact angle that goes down. And you pump in some polymer solution, and it forms this meniscus at the wall, but it also spreads out into the water. And as it's spreading, it's also drying, and it dries quicker as it becomes thinner. And it forms this solid film, which you can roll directly onto a substrate. And so right now I'm working on trying to, develop this into a process. Here's some examples of some preliminary results. And you can see it's rolling and it's pulling it from the meniscus. And so yeah, just to get you guys thinking about how you can use some of the concepts that you learned in this class for your research. And then with that, I'd be happy to take any questions. Yeah, that's it.